Hey everyone, welcome to This Explainer. I'm incredibly excited to get into this today because, well, we're diving into the next massive leap in wireless technology. And I want to be super clear right out of the gate here. We are not just talking about your downloads getting a little bit faster. No way. We're talking about a complete ground-up reinvention of what a telecommunications network actually is. Okay, let's dive into this. I really want you to think about this question for a second, because it's basically the beating heart of everything we're about to cover. What if the exact same network that brings you your video calls could also instantly spot an unauthorized drone near an airport? What if it could see a pedestrian stepping onto a foggy highway way before a driver ever could? Or, even watch your hand gestures to control heavy machinery? I know, it sounds literally like something straight out of a sci-fi movie, but this is exactly the reality that 6G is promising to build.
Section 1. A network that sees beyond faster internet.
So the crucial point is, to give our network this literal sense of sight, we're relying on a totally new concept. It's called ISAC, or Integrated Sensing and Communication. Just like the name implies, the network is no longer just this dumb pipeline for data. It's transforming into a massive distributed sensor. It's using its very own radio signals to map out the physical world around it in real time. It's an absolute game changer for how we interact with our environment. To really wrap our heads around this shift, let's compare 5G and 6G. 5G is fantastic, right? But it connects things that are specifically designed to be connected. Your smartphone, your smart TV, devices that have chips and can actually talk back to the cell tower. But 6G with ISAC, it adds a totally new layer. It can actively sense passive objects. I mean, things with absolutely no electronics, no chips, literally no way of talking back whatsoever. We're talking about sensing a person walking, a car driving, or a piece of heavy equipment operating in a factory. The network goes from just connecting active participants to being fully, consciously aware of everything in its environment.
Section 2. The physics of 6G. Painting the world with radio waves.
So how exactly do we paint the world with radio waves? The amazing part is it's really not magic. It's basically a supercharged version of radar physics that's been around for decades. Let's walk through exactly how a cell tower pulls this off. First, the tower sends out its normal communication signal, right? Typically a continuous wave called an OFDM waveform. Now, while part of that signal heads straight to your phone to load a web page, the rest of it radiates out and bounces off everything in the area. That's step 2. A tiny fraction of that energy might hit a passive object, say a car, and reflect an echo back to a receiver. In step 3, by measuring exactly how long that echo took to return, the network calculates the precise distance to that car. And finally, step 4, by measuring the tiny shift in the echo's frequency, the Doppler effect, the network can figure out the car's exact speed. And this brilliantly illustrates the hardware upgrade making all of this possible. 5G uses massive MIMO with dozens of antennas, but 6G is pushing toward what's called gigantic MIMO. Think of a single traditional antenna like a flashlight with one big, wide beam. It illuminates a general area, right? Gigantic MIMO, however, is like having hundreds or even thousands of tiny, perfectly synchronized laser pointers that you can steer electronically in an instant. This gives the 6G network unbelievable angular resolution. It can tell the difference between two objects right next to each other. With that level of precision, you aren't just detecting a car. You could literally monitor a person's breathing from all the way across a room. Now, the network can arrange its eyes and ears in a few different ways. First, there's monostatic sensing, where one tower transmits and listens. The challenge there? It's kind of like trying to hear a whisper while you're shouting. Bistatic sensing is smarter. One tower transmits and a totally different one listens. This solves the interference issue, but they have to be perfectly synchronized. The ultimate goal, though, the true holy grail of 6G, is multistatic sensing. This is where the entire network works together, multiple towers transmitting and receiving simultaneously to create a flawless 360-degree picture with absolutely zero blind spots.
Section 3. AI at the physical layer. The ultimate balancing act.
Now, doing all of this creates a massive engineering headache. Here's the core conflict. The perfect radio signal to get your data downloaded incredibly fast is usually a terrible signal for getting a crisp, clear radar image of the environment. And vice versa. It is a constant tug of war happening millisecond by millisecond. If you optimize for communication, your sensing gets worse. And honestly, traditional algorithms are just way too slow to manage this for a live network. So engineers are turning to AI. Specifically, a concept called multitask learning, or MTL. Instead of having two separate AIs fighting each other, one for data, one for radar, MTL is one unified AI. It has shared core layers that understand the basic radio environment, and then it branches off into specialized layers for both jobs.
By learning them together, this unified AI finds incredibly clever trade-offs that two totally separate models would literally never discover on their own.
But how does it do it fast enough? First, it calculates a joint loss function. It basically takes the error score for the data transmission and the error score for the radar sensing and combines them into one overall grade. Its entire job is to constantly tweak the live network beams to get that combined score as low as possible. And to do this fast enough for a live network, it uses a brilliant technique called algorithm unrolling. It literally takes complex traditional logic and bakes it right into the structure of the neural network. This allows the AI to live right at the physical layer of the network and make split-second decisions about radio waves.
Section 4. Building the digital twin, the utopian promise.
Now, what's really interesting about this entire concept is what happens when we shift to the real world. When our digital infrastructure is constantly sensing everything around it, the applications are just staggering. Just imagine an autonomous car approaching a blind corner. Its own cameras can't see around the building, but the 6G network senses a cyclist coming and alerts the car instantly. Or picture a factory where the network tracks every millimeter of movement, mathematically guaranteeing a giant robotic arm will never collide with a human worker. It even allows those workers to command machinery with simple hand gestures in a deafeningly loud environment.
All of these applications build toward a massive concept, the digital twin. Because the network is constantly mapping everything, it creates a live, one-to-one digital replica of the physical world. Imagine a digital twin of an entire city, where planners can simulate and eliminate traffic jams in real time. Or a factory twin that predicts exactly when a machine will fail before it actually breaks down. 6G won't just connect our world. Through this live digital replica, it will truly understand it.
Section 5. The Unblinking Network, the dystopian reality. But as with all things, every incredible technology casts a shadow. And an all-seeing network carries an unprecedented weight of responsibility. We really have to ask this critical question. If the network can track the exact movements of a pedestrian who never downloaded an app, never agreed to a terms of service, and never opted in, well, how does that possibly work with our current privacy laws? Spoiler alert, it doesn't. It gives privacy lawyers a massive headache. To understand the sheer scale of this clash, listen to this stark quote straight from Ericsson Research. They state, a consent-based model just seems completely infeasible for this kind of passive, wide-area sensing. Just think about that for a second. The very foundation of our digital privacy is breaking down in the face of this new technology. Let's move on and see how this builds into a massive legal conflict by looking at these two realities side by side. On the one hand, we have frameworks like GDPR, right, which are built entirely around the concept of a person knowingly and willingly consenting to share their personal data. On the other hand, passive 6G sensing collects a staggering amount of physical location and movement data from people who have absolutely no idea they're even participating in a network. This creates a total minefield of severe challenges. First off, who is legally responsible for this data? Is it the telecom operator, the developer building an app with the data, or the government? Second, there's the imminent, very real threat of unauthorized mass surveillance if this infrastructure is misused. And third, the sheer monumental task of securing this new trove of highly sensitive, real-time location data from bad actors. Because of these immense risks, experts suggest that the very first waves of ISAC technology will likely have to stick strictly to enclosed environments or use cases with a firmly established legal basis, just to avoid this ethical minefield. And that leaves us here. The technology to create an all-seeing, unblinking network is no longer a question of if, but when. ISAC is coming, and it's going to fundamentally shift how we relate to our physical and digital worlds. But as we step into this future of incredible safety, zero blind spots, and digital twins, I want to leave you with this profound question to think about. As this technology rapidly approaches, who exactly should be making the rules for an all-seeing network? Thanks so much for joining me for this explainer, and keep questioning the technology that shapes our world.